Right, hello everyone. Hope you can hear me. My microphone's going up and down, so maybe someone in the chat could just say, yes, you can hear me. Excellent. Okay, that's enough. That's enough. Stop now. Right, okay, so welcome to ELEC3208. I'm recording this session, I hope, so these should go up online eventually, so you can use them for revision purposes going on later. So this morning, a little bit of an introduction to what's going on, and we'll just start with some revision. There's a fair amount of revision going forward, but it's quite important that you have this revision ourselves. So no, I'll get rid of me. There we go. So it should all be big now. So a quick overview of what we intend to try and achieve in this course. There are three of us going to be teaching it. I'm going to do the main chunk up until just before Easter, and then the guys will take over after Easter as we go forward. So the overview is really to look at a whole system and just see if we can sort of stitch the whole thing together. So we've got analog and mixed signal electronics going on in here. And so the main sort of systems that we might be looking at, if we start with an input, it might be a sensor of some kind, it might be some other things as well. And we've got a useful signal that we're interested in. Let me just get a pointer up and I can wave at it then. So we've got a signal which is then transduced by a sensor. There'll be some noise coming into this system as well, which is not something we're that interested in, but nevertheless it'll come in. And then we've got to process that in some way, and that usually consists of some kind of amplification, possibly a filter, some form of signal processing. Later on, when we get clever, there may well be a phase lock loop, a PLL, and Kay Lee will be talking about those going forward. And then when we've got that signal in a condition that we're interested in, we might do an analog to digital, send it on through digital transmission to some kind of digital processing system, which can then decide what to do with that signal. And then maybe it will come back the other way, digital transmission, go digital to analog, and that's something we were talking about, and some kind of power amplification, maybe a power amplifier, maybe an actuator, something like that. So that's the sort of main signal flow. We're interested pretty much in everything that's not this red box. But inevitably, we've got to do a little bit of what's in the red box, but we're not really concentrating on that. We're really going to be worried about what's going on in the green box, except the red bit. And to add to that, we need to have a look at power supplies as well. So we're going to do a little bit of work on power conversions and power supplies and how that might help. The other thing that we're going to look at, practical issues such as electromagnetic compatibility. And the rules behind that and why it's important. Some ideas for maybe PCB design and packaging, and also some thermal design, because heat is always the great killer of circuitry. So hopefully at the end of this, you'll have a good idea of how electronic systems are put together with both analog and digital signals, and you've got a good idea how to prepare signals and systems for onward digital processing, and we understand the interface between the two. So there's a sort of a more specific example if you want to look at block diagrams for clock data recovery system in the sort of things like CD players, as they were. So it's the same kind of thing, but it's a little bit more specific there. But you can see how all these things come together: line drivers, transmission lines, phase out loop for clock recovery. We still need power, and we've got everything else going on there. So this is sort of the general idea of what's going on. So unless we hear otherwise, and we may do, this course is evaluated by an exam and a design exercise. And typically, the exam is 2 hours. What happens this year, we don't know. As soon as I find out, I'll let you know. So this is the information for a normal lecture program. By May, it could well be that we're back in exams again, or we could be doing them online, who knows. So design exercise, 20%, we'll talk about that in a few weeks' time, where it allows you to design a system using a lot of the techniques that we've talked about and gone forward. Last year we did a sort of a radar system. I think this year we'll probably do the same kind of thing. It's quite useful. It's only a paper exercise, but it allows you to develop some skills in designing systems and using the stuff that we're talking about here. Quite nice. it says there 3 lectures a week, 1 single, 1 double. Actually, we've got 3 singles this year. Oh, and ignore that date. Sorry, this is last year's slides. The date will change as the details, so don't worry about that at the moment. It's all subject to change. Now, this is the current timetable, as far as I'm aware. At least it was last Friday anyway. We're obviously in this slot here. We've got another one tomorrow, and we've got another one on Friday. The purple things are what might happen after Easter, where we try and go face-to-face, I believe. But that's subject to change, so don't worry too much about the purple slots. Just worry about the orange slots at the moment, and hopefully they're nice and fixed in the timetable now. Okay, so my part will cover the following kind of devices. We're going to talk about signal conditioning, mainly using op-amps, some discrete devices, and we're going to look at different signal sources and how we might want to condition those so that we can present it to ongoing systems. So voltage, current, charge are the sort of things we're looking at. We spent some time looking at filters and how we can implement filters, both looking at a little bit of the maths behind it, just so you've got an understanding of where the filter maths has come from, and then how we can actually implement those equations in different circuit topologies and why some of those circuit topologies are better than others for certain conditions. And maybe we'll talk about some of the practical implementation stuff to make these things actually usable in the real world. Excuse me. So we do some A to D stuff. A lot of this is revision of what you did with probably last year, but then we'll go on and talk about some other types of systems as well. Excuse me. Including sigma delta systems, which are actually quite clever, and they're worth it just for that, really. We do D to A conversion, but turns out there's nothing much terribly exciting about D to A conversion, so we don't do too much about that. And then we get on to power supplies and power amplifiers, which are quite interesting themselves. So at least at the end of this, you'll understand the difference between a Class A and a Class B amplifier system. Power amplifiers imply heat, so we'll look at some thermal design requirements, and we'll look at practical aspects such as electromagnetic and printed circuit. Okay, so Kaylee will be looking at phase-lock loops and how they can be used as tracking filters, demodulators, data recovery is very important application of these phase-lock loops. They're very interesting systems. They've got loads and loads of applications. And then Rumeng will come in towards the end, and we'll talk about transmission lines for HF signals, because even wires, HDMI cables and things, effectively become transmission lines for very high frequency signals. So it's important to understand a little bit about that. Hopefully it's revision, but you won't have seen it applied to cables before. And some look at low noise amplifiers. Where does noise come from? How can we minimize noise? How can we model noise? And how can we sort of mitigate for it? And that should give you a lot of practical, useful knowledge of general electronics and how it interfaces between the analog and the digital world. And this is roughly how it splits down at the moment. Anything after Easter is likely to be variable, so don't take it too much as gospel. And we'll just see how that goes as we go along. Right, so without more ado then, let's start what we're going to do. And we usually start with a little story that shows what's going on. So a lot of words, probably worth reading it a little bit. It's the hazards of not understanding electrical interfaces. Everything in our systems we've looked at so far have been interfaces, systems and blocks connecting to each other and presenting signals in the form that the system, following system, wants to be interested in. So here we've got a story where we have two local men who were seriously injured when their pickup truck left the road and struck a tree near a cotton patch on State Highway 38 early morning, Monday morning. So those details we're not that interested in. They didn't die, but they got wounded. But the interesting thing is that the accident occurred as the two men were returning to Des Arc after a frogging trip, which is collecting frogs. I had to look it up as well. On an overcast Sunday night, the guy's pickup truck's headlights didn't work. So there was a fuse had gone, and they hadn't got a spare fuse, and it was very dark. So they noticed that a bullet was the right size to replace the fuse. So they took the fuse out and replaced the bullet. Now the fuses is normally there to protect systems, If a fuse blows, then you should be suspicious of why it blew. These people obviously weren't. Put the fuse in, lights came on, great, but there's obviously still a problem in there, because after approximately 20 miles, the bullet apparently overheated, discharged, and struck Paul in the right testicle, which caused the vehicle to crash. And there we go. So you can read the rest of it or whatever, but the whole point of the story is that if you use the wrong thing at the wrong time in the wrong system, things will go wrong and not work properly. So just be careful. Right. So with that story in mind, let's think about what's going on in our signal measuring world. We've got a signal to be measured, something we want to know about. We need to turn it into an electrical signal. So a transducer will do that. That's something that turns the signal from the real world, should we say, into the electrical world. It may not be ideal when it does that. It may not put it into a form that we're that happy with. It may be a current, it may be a charge, and we're more familiar with voltages. So then we may have to do, and it may be a very small signal as well. So then we have to do some signal conditioning to get that into a form that we're interested in, to the right size. And then when it's in a voltage form, usually with the right amplitudes and performance, we can then present it to a digital system. And then we can feed it to a digital system, and off we go. Okay, so that's fundamentally what we're going to be looking at, and all the details that goes on in various different cases through here. So signal sources. So there are many different sources of signals. We'll understand voltages. We'll be very familiar with voltages going forward. We'll have heard of current sources. We may not be quite so familiar with them. We may have heard of charge sources, and we certainly won't be very familiar with those. And then there's these other strange things called variable impedance sources as well. And they're quite interesting things to look at. So voltage sources, microphones, all kinds of complex impedances involved. So possibly the most simple voltage source you may come across is a battery. Okay, and if you think about that, that's interesting, because measuring battery voltage is a common thing to want to do in all electronic systems. How much power have we got? It's actually quite a hard thing to do, and we'll talk about that going forward probably. So current sources, photodiodes, very common. We'll look at those in some detail. Such a device will have a large output impedance, often capacitive in nature. So instantly you start to see a bit of a trend here. We're starting to talk about impedances and why they might be important. So we're going to do a little bit about that as well. Charge sources, they're all over the place as well, and we'll look at those going forward. So I won't waste too much time on here. But variable impedance sources are sensors that change their impedance, such as a thermistor. So we've got a change in value of impedance. So it's not generating a voltage or a current or anything else. It's just generating a change in its physical parameters. And so we need to put that into some kind of circuit to try and measure that. So we're going to talk a lot about systems. And there are different levels of system that people will understand depending on their experience. But basically, we're trying to abstract circuits to a point where we get to a point where we can describe them simply. And the simpler we can describe these things, the better it is for us. As engineers, we like things to remain simple, really. So we don't like reinventing the wheel either. So what we will tend to do is put components and devices together into a circuit that we can then reuse in different circuits going forward. So we start with a device. So at device level, that's like a transistor. We'd be interested in the performance of the transistor as a whole. Is it an NPN? Is it a PNP? You know, how large is it? What's its frequency, maximum frequency it can operate at? That kind of thing. And we'll combine those devices into a circuit. So here's a little circuit diagram here of something. And we can define the performance of that in a block. And so we can start to abstract straight away and say, we're not really that concerned about what these transistors really are. We're interested in the performance of this block overall. So we can put different transistors in, maybe get slightly different performance, but as long as we know what's in the block, we're going to be fine. And these blocks then turn themselves into architecture. And obviously something like an op-amp is an architecture because it's made up of loads of different transistors. And we're not interested in what's in the block. We're just interested in the overall performance of the block. And that can lead us to an architecture here, which is some kind of switching integrator circuit here. And what's actually in these triangles we're not that interested in. We just want to know that they perform the same as each other. And that leads us then to a whole system where we take a lot of the blocks and in different architecture blocks, bolt them all together to make a very complicated system. And we can model this at a system level as long as we're happy of the performance of each of these blocks, which relates back through the circuits and down to the devices. So it says blocks can be replaced with different architectures, but the same functionality, and the whole system should still perform the same. The devil's obviously in the detail there, though. So we start by looking at amplifiers. So hopefully it's revision, but I know from experience that some of you will be very good at amplifiers, and some of you will say, oh yes, amplifiers, I think I've heard of them. So we'll spend a little bit of time just going over what they are and why they're important, and then at least we'll know when we come to the more complex stuff that everyone's on the same page from that respect. So amplifiers are really important. They tend to be the mainstay of signal processing, so they're really important. And in the world of amplifiers, the operational amplifier, or op-amp, tends to be really common, and it's also very convenient for processing most signals. Not all, but most. Okay, so the op-amp is a good approximation to the ideal amplifier. So remember that the ideal amplifier, which is just a block, remember, has perfectly controlled gain, infinitely large input impedance, and we'll look in a minute as to why input impedances are important, just to remind ourselves. It has zero output impedance, and ideally, again, remember this is ideal, has an infinite bandwidth, which by definition includes DC. All right, so with bandwidth, we're talking about frequency, responds well across all frequencies, including DC, which is zero frequency. Now, the ideal op-amp, which is just a class of amplifier, or is just a device that can make amplifiers, actually has an infinite voltage gain, which is different from a perfectly controlled gain, differential input, and the reason for that we'll talk about in a minute, infinitely large input impedance, which matches this requirement very nicely, zero output impedance, again matches that nicely as well, and infinite bandwidth. And remember, this is ideal op-amp. So the ideal op-amp has a lot of commonality with the ideal general amplifier, but they're slightly different from each other, as we'll see. So why do we want infinite voltage gain in an op-amp? It sounds like a very bad idea, really. But what it does is it allows easy use of feedback. And feedback is really helpful because it allows us to control the gain of a system really, really well. So if you think back to how feedback works, and I hope you remember this, the higher the open loop gain, the less effect the amplifier's characteristics has on the closed loop performance. So in a simple case then of an inverting voltage amplifier, single op-amp amplifier, it doesn't matter what op-amp you use, you can make a controlled gain just by using two feedback resistors that you know the value of. The gain of that system has nothing to do with the parameters of the amplifier at all. You can use any amplifier from any op-amp from any manufacturer, pretty much, swap them all out, and it will have exactly the same closed loop gain because it has infinite voltage gain in the op-amp. Okay, so this is a really important idea, and we'll look at that as well going forward. So a differential input is a requirement if we want to measure at DC. And again, we'll talk about this in a bit more detail as well. But it does come about from the need for biasing currents in the amplifier. So you have to have a little bit of knowledge about what's in the amplifier. And remember, it needs some bias currents, and you have to make sure that you don't build one that doesn't have bias currents allowed in. But to get down to DC, that means that you cannot use capacitive coupling to separate the bias signal from the signal you're interested in. So we have to have a DC connection. The only way to do that is to have a differential input. And we'll talk about that again and get some detail on that because that's a really important concept too. And an large input impedance, which means no current goes into it, is useful to avoid loading any preceding stages. It also makes it easy to analyze things. If you go think back to virtual grounds only exist because of infinitely large input impedances. But it makes cascading amplifiers, which means bolting system blocks together, much easier, because if you also have a zero output impedance, when you connect a zero output impedance to something that has an infinitely large input impedance, there's no loading at all, and therefore it's a perfect system connection. Right, so there's a lot in that. Hopefully it's revision. We can look at why loading is important, and this will maybe get the idea over. Right, why is loading important? If we have a signal source, and here's a LT Spice model of a signal source. It's a voltage source, and it's generating 5 millivolts of signal. The sensor itself is modeled by a resistor and a voltage source connected as a block. So this is our sensor, and it has an internal impedance of 10 kilo ohms. Okay, so if you connect this to a measuring system that has an input impedance of 100 ohms, so here's our measuring system connected on, it's got 100 ohms input impedance, and we're measuring the voltage at this point here, what we've created is a potential divider. So it's a potential divider, 5 millivolts here is going to drive a current through here. This current will cause a voltage drop over this resistor. It'll also cause a voltage drop over this resistor, and so we're measuring the nodal point of this potential divider, which isn't this voltage here because it's been dropped across this resistor here. And you can work that out. In this case, the voltage measured will be 5 millivolts, which is the driving voltage, times the potential divider, which is 100 over 100 plus 10. Okay, that comes out at 0.0495 millivolts. So although you've got 5 millivolts here, you will only measure 0.0495 millivolts here because it's loaded. And so by the simple expedient of then putting an op-amp buffer into the system, so remember this has a gain of 1. It has the input impedance of the amplifier, which is very, very high, ideally infinite. And it has the output impedance, which is very, very low, ideally 0. So here, that means there's no current flowing in here. If there's no current flowing in here, then there is no voltage drop across this resistor. And if there's no voltage drop across this resistor, then the voltage here must be the same as the voltage here. This has a gain of 1, so the voltage here is the same as the voltage here. Likewise, we're now driving a current into this 100 ohm measuring system, but because the input impedance here, or the output impedance here is 0, there's no voltage drop here, so we just measure this voltage output. So suddenly we're measuring exactly the voltage we're interested in, and you can see here we've got 5 millivolts going in, and we're measuring at V out 0.004999995. So there you go. This is in millivolts up here, remember. And the nice thing about this is now you don't care what this value is, and you don't care what this value is, because you've buffered it in here. And that's the power of putting buffers in the way. Suddenly you don't care about what the rest of the system is doing because of high input impedance here and the low output impedance here. Okay, so I hope that clarifies things about why impedances, output impedances, input impedances are very important. It's quite a simple case, but it's something that people seem to forget all the time. Right, so a little bit of history, because op-amps are obviously quite important. The op-amp, we would know it as an integrated circuit, which is a little black thing with legs. But the op-amp was not originally an integrated IC, because it was invented before ICs were invented. Originally, it was made as a valve amplifier back in 1952. And valves were sort of glass cylinders with vacuums in them and electrons actually flying across the gaps. And it is what is the only type of amplifier that could be made before the invention of the transistor. So people tried very hard to make it do things. Even in those days, people knew what they wanted, but making it do it became a bit trickier. So these systems operated on plus or minus 300 volts. They could move their outputs by plus or minus 50 volts, which is a good percentage of this, but it's not ideal. The open loop gain was about 20,000. Remember, we're looking for infinite gain. Its power consumption was 3 watts, which meant it could heat a room. And it cost a lot of money in those days. $24 nowadays will be about £20,000 probably. But nevertheless, people liked it. It was a good idea. Once a transistor came along, more reliable circuits could be designed, but we were still making them with discrete transistors. So we're taking individual transistors and soldering them together. And only today I discovered a design for a 741 op-amp that had been made in individual transistors, which is an interesting idea. But you put the transistors together in a little circuit board, and then you pour plastic on them so it looks like a big circuit. They work quite well. We've now got an open loop gain of 40,000, so twice as much. Ran on plus or minus 50 volts. Much easier to cope with. And worked reasonably well. Right, I'm sorry about that. Can you hear me again? Yep, good. Yeah, sorry. At the my internet, I think it was my internet connection crashed. So back again. Hopefully it's still being recorded. Yes, looks like it is. Great. Okay, so yeah, we're doing all right. So this is roughly how you can make an op-amp. It's a bit complicated, and we'll talk about what goes on here. But we've got differential input. That's the important thing. We've got a minus and a plus input, and then we've got an output. So this is quite a simple device. The first successful device was the 741, which you'll have done in labs. And 741 internally looks like this with quite a few transistors in there. And you've probably looked at this in other courses as well. We can simplify that down a little bit, and we end up with a differential input, which allows us to connect DC signals in here, but we have to think about the biasing. We've got a gain stage. So this is called a Darlington pair or a super beta transistor, which gives us a huge amount of gain. And then we've got an output stage, which is basically a common collector amplifier, which gives us some current gain rather than voltage gain. And this gives us the output impedance that we're interested in. The output impedance of this system is not great, but internally it's all sorted out. The rest of the stuff is all to do with biasing. Biasing is really important in ICs. So we would call this a long-tailed pair because it's got a tail on it down here. And that would then drive this gain stage over here. So we've got a differential input, so a plus minus input coming in. The difference between these two inputs is turned into what's called a single-ended output. So this is the only output, and it's referenced to this supply here, which is never moving. So this is just going, just reference to that. That is then amplified hugely, and then it goes into this buffer stage, which is called a push-pull stage, to allow us to actually get some current out of this device. And the overall gain of this whole system is around about 200,000, which is close enough to infinity to be really useful. More modern ones have much higher gain, but 200,000 is enough. The only interesting thing is this capacitor in here. I'll say the only interesting thing. One of the interesting things is this capacitor in here, which allows it to become stable under nearly all conditions. Because it becomes a short circuit at high frequencies, so actually gives us a feedback path that becomes a short circuit at high frequencies. So the gain is lost because it effectively shorts these transistors out. Right, so why are we interested in differential inputs? Differential inputs, differential amplifiers in general are really, really useful. I'm sorry if I'm creaking, I've got a very creaky chair here. So this is what's a circuit known as a long-tail pair. The interesting thing here is we have a current source in the emitter. So this is the emitter current, and it's a current source. And the interesting thing about current sources is they give a constant current, and it doesn't matter what voltage across them, they will give you a fixed current, irrespective of what you try and do to it within reason. And this is the way of biasing these transistors. So we have to have a certain amount of current flowing through these transistors for them to actually act as amplifiers. Now, in previous work that you probably looked at, you will have put a bias current into the base which is then be amplified and giving us an emitter current, which allows this thing to operate. We can't do that with an input that we wish to connect to DC, because there's no way of distinguishing our bias current then from the input signal. So we have to bias in a different way, and the biasing is done by a current source in the tail, which is a fixed current. And this is okay, but if you only had a single transistor amplifier, so if we got rid of this part over here and only had this, so it looked like a single transistor amplifier, it would never amplify anything, because the current through it would always be constant, because it's been fixed by this current source. So that's no good to us, which is why we have to have another transistor opposite to give us a chance of actually varying the currents through these transistors. They're still fixed by the current here. So this current down here plus this current down here must always add up to this current here, which never changes. So this is constant. And the only way that that can happen is if we have different currents going through these transistors. So if this current falls, this current must rise, and then it must still add up to give us this fixed current constant here. And that's the nature of the differential amplifier, that one signal goes up, one signal goes down, and then we can get a difference in voltage between these 2 points, because we've got a different current going down here compared with a current going down here, and therefore we've got different voltage across this and a different compared with the voltage across here, so we can measure a difference in voltage between these 2 points in the collector. If we put the same signal into both of these, so a signal goes up on this side and the signal goes up on this side, all that tries to happen is that this transistor will say, my signal's gone up, I want more current to go through me, please. This one will go, my signal's come up too, I want more current to go through me. And the current source is going to say, well, you can't have any more current because I'm fixed. So all that happens then is the voltage at this point rises to maintain the same VBE across these two. There's no change in the voltage between these 2 points, and you don't see any change in output. Okay, only different signals will give you a change in the output. Right, so I've jumped the gun because this is what this slide is telling you. So the only thing to add from my description of a couple of minutes ago is that we would term a signal that rises by the same amount on both sides as a common mode signal. The mode is common, it's happening at both inputs at the same time, and the other input is called a differential mode input, because the signal is going up and this one is going down. And that's the only interesting one in many ways, but the difference between the two becomes really, really important. You might think, well, okay, common mode, nothing's happening, it's not amplifying anything, that's not important. It's actually really, really important, because if you think about it, most noise signals that come into the wire here will also be picked up in the wire over here as well. So you've got the same signal, same noisy signal on both sides of this system. And what happens when the same noisy signal comes in on both sides is the system goes, well, I'm not amplifying that because it's the same on both sides. So the output doesn't show the noise. So as long as you can arrange for your signal to be differential and most of the noise to be common mode, this actually acts as a really good filter and is a good way of getting rid of lots of potential problems, particularly in factory environments. Right, so difference amplifier, which is what it is we've been looking at. We would have 3 terminals of interest. We've got our 2 input terminals, and we've got an output terminal, and we've got 2 power supplies, usually a plus and a minus. We've got 1 output terminal, so we would term this a single-ended output, and you might term the input as a double-ended input or a differential input. And you can define the difference voltage formally, mathematically, as the difference is VA minus VB. The difference between these 2 terminals, and we can then define the common mode voltage as the sum of VA plus VB divided by 2, so it's the average between these 2 effectively. And the difference amplifier tries to implement this equation. Whatever the difference gain factor is multiplied by the difference voltage plus whatever the common mode gain factor is multiplied by the common mode voltage. So this is what all amplifiers are actually implementing, is this type of equation. One for differential signals, one for common mode signals. So if you're wondering why those are defined as they are, it's actually very tricky to find why it's defined as that. But I've had a look around, and this is what it comes out of it. So if you've just got two general purpose signals, V1, V2, which could be doing anything, they could be up and down, they can be independent of each other, whatever. You can say that they can be represented by the equivalent circuit of this, where you've got a common mode signal and difference mode signals, where the difference mode is just the inverse of the other. And so that, in general, can be replaced by this, in general. And they are identical circuits when these conditions are the true. So we just say the true and then work out what's going on. And that way, that leads you to these definitions of difference and common mode voltages. Okay, so a lot of you probably won't care about that, but some of you will be interested in the detail, and that's where the detail comes from. Quite straightforward, but you do have to think about it a little bit. So why is it good? So I've told you a little about why it's good already. If a single-ended signal is noisy due to additive noise, a single-ended amplifier will amplify both the noise and the signal equally. It can't tell them apart. Just seeing one signal, it'll just amplify as best it can. But if you can get a transducer or a signal that can give a difference mode signal as its output, then when we add the noise is common mode and the signal is differential mode. And that allows us to come up with a sort of a goodness factor between these two gains, which is called the common mode rejection ratio. And that's simply the differential gain, which is usually high, divided by the common mode gain, which is usually very low. And so the bigger the ratio here is, the better you are at rejecting noise. And quite often we'll put this as a dB signal, so 20 log magnitude AD over AC. And you can plot that on a log chart, and you get this off the data sheets for all amplifiers normally. And you can see here that common mode rejection ratio dB is 120 dBs for very low frequencies, starts to fall away with frequency quite quickly, as everything does with op-amps. So be aware that op-amps do their best, but they're not that good at high frequencies. At high frequencies, we still need to go to discrete transistor amplifiers normally. Right, so the input amplifier we're looking at, and we'll look at it in a little bit more detail. We've got a difference voltage coming in, which is VB1 minus VB2, so the difference between these two inputs on these bases as transistors. And then we've got the common mode, which is the average of the two inputs, just the average of the two. And also, if the transistors are well matched, and this is important, and this is why op-amps are always now integrated, because we can make the transistors to be very much the same. We can say that IC1, collector current in C1 there, is equal to IC2, which is equal to IE over 2. So IE is the value of the current source, splits into two, and half of it comes down here and half of it comes down here. And that works if the transistors are well matched, and we want them to be well matched. Because one of the other interesting things is that if you've got transistors like this on a single substrate, so they're very close to each other on a single piece of silicon, then the gain of these things we know changes with temperature. Everything is affected by temperature, but temperature becomes a common mode signal. Yeah, the variation in temperature causes the signal to change equally in both sides, so it's matched out. To recap, does well matched mean they share virtually the same characteristics? Yes. Well matched is a euphemism for identical. The holy grail of integrated circuit design is to make all your devices, all your transistors that you've made onto a chip, absolutely identical, because then all this maths becomes ideal and wonderful. And that's why it's hard to make an amplifier, a well-matched amplifier, from transistors that you get out of the drawer in the lab, for example, because first of all, they've all come off different substrates because they've all been chopped up and mixed in the box. So they'll all be slightly different in terms of their GM or their various currents or their voltages. And also, if you put them onto a circuit board, there's a good chance they're going to be seeing different temperatures. Even small temperature gradients can make a difference. And that just makes the common mode gain high, or higher than it needs to be. So well matched, yes, means identical. And the more identical you make these things, the better. Becomes important like in things like oscillators as well, because any variation there means the frequency changes, and that's usually not what you want. Right, so how do we do a small signal analysis? Well, a hybrid pi is what we've done in the past, so we can try looking at that. So we have to think back a little bit to what our hybrid pi model is from maybe first year or possibly second year with Kushik. So our transistor is this bit, and it's an equivalent input impedance, which we call R pi, and it's an output source, current source, which has the value GM, which is a constant, well, roughly a constant within the transistor, depending on the bias conditions, and V pi, which is the voltage across this input resistance. So whatever the voltage across here is multiplied by GM, and that gives us a current through this device here. And then we use RC to turn the current into a voltage, and we can measure the voltage at this point. So in the case of the differential amplifier, for small signals, so remember small signals, we would short circuit any power supplies because it's a partial superposition analysis. So the power supply here becomes shorted to ground. I've got ground down here as well. And you can start to see a certain amount of symmetry in this representation. Right. The current source has been replaced by this resistance, which is the dynamic resistance of the current source. Remember, we had a current source that was, we were saying that that's the fixed current, and that's all we're going to get. It has a certain impedance associated with it. In an ideal world, this impedance of an ideal current source would be infinite. So RE tends to be a very big resistor or whatever. So that's sort of what we're looking at. It turns out that it's not actually that important when we do the analysis. So if we break this into the two signals, so we've got a differential input and a common mode input. If we consider just the differential input, we would say that VB1 equals minus VB2. So these are the two inputs. VB1 here, if that goes up, VB2 goes down by the same amount. And by looking at this, we can then see that VE here is always going to be 0 because it's halfway between whatever this voltage is and whatever this voltage is. And if this one goes up, this one's going down by the same amount. So VE always stays 0 because it's always halfway between the two, and halfway between the two is always 0 for an equal differential input. Which means if there's no voltage across here, we can effectively ignore it for purposes of this analysis. If there's no voltage across it, there's no current flowing, might as well not be there. So we end up with a simplified version of the circuit, which allows us to be treated as two separate halves. The gain of each half is then going to be GM-RC minus GM-RC, and you can work that out from down here. It's quite obvious, or we can get it from first year analysis notes. And if we combine both halves, we get BC1 minus VC2, which allows us to run it through the normal wheel, and we end up with the differential gain becomes minus GM-RC, which is really interesting because it means that the gain is controlled by effectively the value of RC. And if we can make RC big, then we can make a very, very high differential gain. So that's the basic sort of analysis for this amplifier. And it comes out to be the same, if you go back to the first year notes, as a non-bypassed common emitter amplifier. So and that's an interesting result in its own right. If we then put a common mode input into our small signal model, VB1 equals VB2 because it's common mode. If this one goes up by the same amount. And therefore, by symmetry, VC1 equals VC2. So VC1 is here and VC2 is here. So what we can actually say is that whatever's going on this side of the circuit is the same as what's going on this side of the circuit. So effectively, we could say that these are paralleled up. So if you can imagine, if you take this half of the circuit and just fold it over on top of this one and join these two inputs together and join the outputs together, you end up with this, because these two resistors, if you fold it over, become in parallel with each other. So they halve their value, obviously. The current sources add up, and our pi becomes half the value as well. So we can analyze this for a a common mode input as this, which is this thing folded over on itself from various inputs joined together. And this, when we start to look at it, looks just like common emitter stage, but with an unbypassed emitter resistor. And if we remember going back to the first year, we can get a rough estimate of the gain of this as being RC over RE, effectively. In this case, it's RC over 2, because RC has become RC over 2. So it's RC over 2 over RE, because there's some feedback involved. So if you don't understand where the feedback's coming from here, go back and have another quick look at the first year notes. But what we've now got is something that has a common mode gain, well, which you do it properly becomes that, but simplifies down to effectively, in this case, half RC over RE. So depending on the value of these resistors, this can be a very low gain. And ideally, we would like RE to be very, very large, ideally infinite, because that would make the common mode value 0. Remember, RC from the previous slide told us what the gain was for the differential one. So we want that to be big as well. And we want this one to be even bigger. And that will give us the system we're looking for. So total gain for both differential and common mode. So total output voltage is whatever the gain is for the difference mode added to whatever the gain is for the common mode. So we've got GMRC, which is controlled by RC, which we can make big. So VD, the whole gain for that part can be very large. And then we've got RC over RE. And if we can make RE even larger, we end up with a very, very low gain for this part of it. And that's what we want. Ideally, we want this to be infinite, and we want this to be 0. We're not going to get that perfection. But what we can do is try and think of a way of making RE be very, very large in a useful way. And we do that with something called an active load, which is basically a current source. We could put a very big resistor in there, but if we put a big resistor in there, we have to provide lots of voltage, because even small currents going through it, bias currents, will drop lots of volts across it. So that's not an ideal solution. So we want dynamic, which means it's only got a high impedance for changing currents. And this is what we end up with. Simple model of the input stage of the op-amp. We've got, all right, where do we start here? Okay, so what we will do, so the picture on the left is what we started with and what we would probably understand as long tail pair. We've got our current source in the tail, we've got our 2 input transistors, and we've got our output resistors here, and we measure the voltage across here. So this is what we've been looking at up till now. What actually happens in the 741 is that it's inverted and is fundamentally driven by PNP transistors rather than NPNs. So think back, if we swap NPNs for PNPs, everything just gets inverted. So now we've got our bias source at the top. We've got our currents going through here, and then we've got an output reference to a negative supply rail. So it's just been flipped over. This is just what they did in the 741. It's just because that's what they had in those days. They had PNP transistors mainly. And so if we look at this in simple terms, so this diagram here is the one that's being converted over here. We've got our current source coming down here. We've got our 2 input transistors, and then we've got this thing called an active load down here. And what we've done is we've connected effectively a current mirror. So this part here is a current mirror. We've got this transistor over here with its collector connected to its base, which makes it into a diode, if you remember back to part 2. So this is looking like a diode. And whatever happens here, you change the voltage here, it goes up. We get more current going down here, more current going through the current mirror here. This is connected to this transistor. It's got exactly the same VBEs because of the way they've been connected. So this one wants to have exactly the same current as is the one going through here. But remember, the voltage on this one has gone down with respect to this. And so this transistor is saying, in this case, I'd like less current, please. This current source is saying, well, I'm going to have the same current running through here. So the only thing that can happen is more current can actually come from the load down through this resistor to make up the difference. And that's how we turn it into a single-ended thing. This is fixed current, and it's defined by the voltage across here, which is defined by the difference input here. That fixes a current through here. This one tries to match the current, but it obviously can't because this transistor is going the other way. And if this one's asking for less current, this one's asking for more current, and vice versa. And the only place that that spare current can either go is either out of here or in from here. And that's what turns this thing into a single-ended output. And the voltage is then generated over this load resistor, which allows us to get a single-ended signal. So it's quite clever. There's a lot of cleverness going on in this system. But that's what happens with an ideal one. Non-ideal ones are the things that we have to deal with in the real world, and we end up with some issues. And because of the well-matched problem or non-well-matched problem, we would find that we end up with an input offset problem, which effectively means that if you put 0 volts in differential to our amplifier, you would expect to get 0 volts out. But because of very small mismatches in our very well-matched transistors, you will find that for 0 volts in, you will not get 0 volts out, but a small output voltage. And that may or may not be important. And we'll look at why or why not it might have been important going forward as well. And on the offset voltage, this problem is made up of 2 parameters. One is called the input offset voltage, and the other is a voltage due to input bias currents. And we're going to look at those in a bit more detail. But I suspect we've had 52 minutes of this now. It's probably a good place to stop for today. We can pick this up again tomorrow and go forward. What I'll do is I will upload these lectures to Blackboard in chunks. But as you can probably see, the slides are in a big file. But I might try and chop out the slides into little helpful chunks as well to allow you to maybe do some revision. But this should all just be revision at the moment as we go anyway. So I will stop for today and we'll pick that up tomorrow. I hope that's revision for you, and it's giving you a bit of a taste of some of the interesting things that might come forward. I think it's really interesting to start from the basics and run forward because then you've got a chance of understanding what some of the more complex circuits are really up to. So, okay, so as I said, I'll stop there and I will see you all tomorrow. Hope you enjoyed that.